All right, so this will be the last video here, and we just have a little bit left to cover. So for this one, we are continuing to talk about the determinant and its effect on area. So we showed that if you take the unit square in 2 space, and if we plug it into a transformation, we get a parallelogram. And then we showed if you have a parallelogram determined by 2 vectors, the absolute value of the determinant of those 2 vectors is the area of that parallelogram. So how do we unite these 2 concepts? Well, this unit square you can think of as being determined by your standard basis vectors, I and j. Okay? Then the linear transformation is going to take I and j and map them to these 2 vectors here. So what that means is that if I took the image of I and j under my linear transformation T of A, I'd get these vectors, and then if I put those vectors into the columns of a matrix like we do to come up with the matrix A, and then if I took the determinant of that matrix, I would get the area of this parallelogram. Now that's interesting, but a consequence of that is much more useful. This only concerns squares and parallelograms. However, because of the way linear transformations transform space, you know, these grid lines are kept parallel and equally spaced, a consequence of that is that if I took any general region, whether this is a square, a circle, or some big blob looking shape, and then plugged it into my linear transformation, the effect, or the comparison I should say, between the original region and its image over here will be proportional to the change in this area to this area. So in other words, let's suppose that a linear transformation takes a unit square, and then when transforming it into a parallelogram, the result has double the area of my original unit square, which is not the case here, but you know, in a different example maybe. Then what that would mean is that any other region that I could draw over here, once plugged into my linear transformation, would also end up with double the area of the original. So that lets us talk about the area of any type of transformed region relative to the area of the original region that we started with. And I'm stating that as a theorem right here. In that example, I said, what if the area gets doubled? But then in that case, the determinant would have an absolute value of 2. In more general terms, if R is any region in R2, and if A is any 2 by 2 matrix, and then S, and if we let S be the image of R, so it's the region that we get from transforming R using this linear transformation, then the area of S will be, this should be an absolute value, the absolute value of my determinant of A times the area of R. Okay, let's look at an example to confirm this. And when I typed this up, I forgot to leave myself enough space here, so I'll probably have to jump onto another page for a second. Let's let this matrix A be 2, 0, 0, 3. I want to find the area of the image of the unit circle under T of A, and then I want to confirm my result geometrically. Well, first of all, the unit circle has an area equal to pi times 1 squared, which is just pi. That's the area of a unit circle, right? According to this theorem, if I want to transform this circle using this linear transformation, which we're going to show stretches that circle into an ellipse, then the area of that ellipse can be found by simply multiplying the area of my circle times the determinant of this matrix. So what is the determinant of that matrix? 2, 0, 0, 3. Well, it's just 6. Okay? So the area of the transformed unit circle would be 6 times pi, or just 6 pi. Okay? Now, how do we confirm that geometrically? Well, let's take a look at our unit circle first of all. Okay, notice that Oop, I'm off the screen there. Here's my unit circle. It's not drawn well, but just imagine that it's a unit circle. If it's a unit circle, its radius is 1. So notice that my I can draw two vectors in here as radii of this circle, and that would be I, because that has a length of 1, and that would be j. So the unit circle is determined by these two unit vectors, okay? But now let's think about my matrix A. What was A? A was 2, 0, 0, 3, okay? 2, 0, 0, 3. And remember, the columns of this matrix represent the images of I and j. So I is going to become 2, 0. In other words, I just doubles in length. So I end up with 2i right here. J gets mapped to 0, 3, which looks like j but tripled in length. So I end up with 3j here. This produces that stretched out ellipse, which I did a terrible job drawing just now. Okay, but notice the length of this part of the ellipse right here is 2, and the length of this part would be 3. Now, in case you didn't know, if you have an ellipse where with a center here, and if this is A and this is B along the major and minor axes for that ellipse, there's an area formula that we can derive. We do this in calculus oftentimes, derive this area formula. The area is equal to pi times A times B. I'm not going to derive that here. That's more of a calculus thing, but you can look that up. Pi AB will give you the area of that ellipse. Well, notice here, A is 3 and B is 2. So the area of this should equal 3 times 2 times pi, or 6 pi. Same thing we got using the determinant approach. It's confirmed geometrically. This would work, though, with any linear transformation, even if the circle was not just stretched into an ellipse, but maybe there was a shear applied to it, so it stretched it, in a different direction as well. We would still get correct areas using this technique. Pretty interesting. All right, last thing I want to talk about in this connections sequence of videos, inverse matrices, because that was a big topic in Chapter 1. How do we make sense of inverse matrices geometrically speaking? Well, remember, the definition of an invertible matrix is a matrix that you can multiply by some other matrix that we call an inverse to get us back to the identity matrix. So let's think about the identity first. If I is the identity, I times x is equal to x for every vector x. So if we think of I as the 2 by 2 identity matrix, what does it do when you multiply it by a vector geometrically? Well, the answer is nothing. It doesn't rotate it, it doesn't scale it, it leaves it alone. Okay? But now, let's use this idea in conjunction with the idea of invertible matrices. Let's suppose A is an invertible 2 by 2 matrix. Then Ix can be written as A inverse A times x, because this would multiply to the identity. But then if I were to use the associative property, I could write this as A inverse times Ax. Now remember, we think of this as a composition of two linear transformations. First, I plug x into the linear transformation that multiplies it by A. That will most likely change x into some other vector. Okay, so I can think of, if I think of this vector here as x, then when I plug that into t of A, it should take that vector and do something to it. So let's say it rotates it and scales it, and this is what the output of that might look like. But then if I plug that new vector into TA inverse, what this is saying is that the result should look like Ix, which is just x. In other words, it should reverse what happened here and take me back to that vector x again. Okay? So an inverse matrix, when we think of it using a linear transformation, is a linear transformation that undoes whatever a different linear transformation was able to do. Okay. How then do we make sense of singular matrices, matrices that are not invertible? Well, in the case of a singular matrix, remember, a matrix is singular or not invertible if and only if its determinant is equal to 0. Now, what does that mean based on our discussion of determinants previously? Well, again, we said before, in the case of a linear transformation that takes vectors I and j and maps them to these images, if the matrix has a determinant of 0, then the columns of that matrix, a 2 by 2 matrix specifically, the columns of that matrix are proportional, which means that the two output vectors here are parallel to each other. And so what that's going to do is cause all of your space R2 to collapse down to a line. Let's say for a second that, let's see if I could draw this. Here's R2, and let's suppose that I and j map to these two vectors right here. So that's the image of I, this is the image of j. Well, going back over here, remember the image of I and the image of j determine what's happening with all of these grid lines. So all of these grid lines here are going to be parallel to I, and all of these other grid lines will be parallel to j. But what's happening now is it's taking all of that space and collapsing everything down into a single line like this, which means we've lost a dimension in our space. What that ultimately means is if you have some vector that's mapped, some vector x in R2 that gets sent into this linear transformation, then it's going to be collapsed down onto this line. But then to try and reverse that, it turns out is impossible. In other words, you cannot recover two-dimensional space from a one-dimensional object like a line. Now there's a lot more depth to that idea, and it's really beyond the scope of what I want to go into in this class. So I'm going to just kind of let you ponder that, but hopefully intuitively on some level that makes sense. Okay. So that's going to be it for this section. Next up is going to be chapter 4.